2 o'clock, so I'm going to get started. Good afternoon, everyone, and thanks for joining us on our call today. My name is Nicole Van Wert from Transcat, and I'm going to be your moderator. The webinar topic today is Vibration Testing 101. It's being presented by John Bernet from Fluke. John is a mechanical application and product specialist for Fluke. Using his 30-plus years of experience in maintenance and operation of nuclear power plants and machinery in other plants, John has worked with customers in all industries implementing reliability programs. He is a certified Category 2 vibration analyst with over 20 years of experience diagnosing machine faults and a certified maintenance reliability professional. He has served in the U.S. Navy as an electrician for 12 years as well. We expect our presentation to last roughly 30 to 45 minutes, and then we'll answer any questions that have been submitted during the presentation. During any time, you can send questions through the question box to the right in your webinar controls. I also wanted to mention that this webinar is being recorded. Each of you will receive a follow-up email with a link to the recorded webinar and the slides of today's presentation in just a few days. At this time, I'm going to turn the presentation over to John.
Hello, everybody. This is John Bernet, and thank you very much, Nicole. So let's go ahead and get started. So what we're going to talk about today is why vibration testing is important, the difference between different vibration tools, who can best use which of the tools, and when to use the tools, and how vibration testing is performed. So hopefully there won't be too much of a delay in the screen, so I'll try to keep moving. But first we're going to talk about why is vibration testing important. There are several different topics, and I'll go through these briefly. One is predictability. You know, studies have shown that having an early warning of impending failures gives a maintenance staff time to schedule repairs. And there are a lot of different examples. I won't read all the example case studies, but feel free to read them as we go through this, and get a copy of the PowerPoint as well. Safety is a big feature. You know, if you've got a machine that has some type of a failure, the rotating components, or maybe the it might be an environmental hazard. You know, it might be something in the piping or something in the ventilation that we don't want to get released. One of the biggest ones is always going to be revenue. You know, the bottom line. Production losses are very, very expensive, you know, and if we can have the plant run longer, that's millions of dollars to customers. And so we always want to think about keeping machines running. Increased maintenance intervals, the time to repair machines. You know, some machines are hundreds of thousands of dollars. Some aren't as much. Sometimes a small machine that doesn't cost very much takes down a big machine that does cost a lot, or stops production and the whole plant is shut down. So there's a lot of different reasons. Reliability in a plant, in some plants, is critical. You know, if you have cancer-making drugs, and if the machine is down at all during the process, it can wipe out the whole production run, which could be millions of dollars. So cost savings from energy waste. A lot of people don't think about, they think about production, they think about maintenance cost, and but what about energy savings? Just having a machine a little bit out of balance or misalignment can cost thousands of dollars a year in energy savings. Peace of mind. What machine keeps you up late at night? Let's see if we can find a way to make that machine more reliable and easier to maintain. So what about the different vibration tools? There's a lot of different tools out there, and let's talk a little bit about a typical plant. So let's talk about if we took all the machines in a plant and we put them into a pyramid. At the top of the pyramid are a few machines that require a vibration expert, okay? If you think about a vibration analyzer and a vibration expert, they're really only required for the top few machines. And these types of machines are like paper machines, machining tools, turbine generators. But the rest of the machines in the plant, the other 90 or 95% of the machines in the plant, are just simple mainstream machines: motors, pumps, fans, compressors, blowers, gearboxes, things that are really pretty constant, and they don't have a lot of variables to them. Those are the kind of machines that we can test with a vibration tester, and we'll talk a little bit more about a vibration tester and a vibration meter. But first of all, we want to kind of show you which machines are going to be used, which testers can be used on different machines. If you think about the bottom level machines, the machines that are typically small and expendable, a lot of people ignore these machines, but sometimes these machines can cause a lot of energy waste, or they can cause other machines to fail. So these are the kind of machines that we might want to monitor with the vibration meter, so a screening tool. So we're going to talk about the three different levels of tools and of people and of skill sets and of machines. So let's talk a little bit about that, because how are we going to monitor all of the critical and important machines in a plant, especially with our dwindling resources? Every year we have to do more with less. We have larger demands, more production. We have more and more people are retiring, and they're not being backfilled. So how do we maintain all of these critical machines without having a lot of resources? Think about the medical industry. How do they do it? Well, they use nurses to screen out the first problems, and then if they can take care of it, then that's great. If not, they bump it up to the doctor. The general practice doctor can take care of most of the faults, most of the problems with patients, and then it gets bumped up to a specialist. Let's do the same thing with our machines. Entry-level technicians can use screening tools to look for potential problems. Let's screen out the 80 or 90% of good machines. It doesn't make sense to spend time analyzing healthy machines. Next, we'll use technicians that'll use a vibration tester to find the root cause and diagnose the fault. And then finally, bump up just the few problems that we can't do with our tester and our meter to the expert for the complex faults. So the benefits of tiered maintenance is we can reduce the number of work orders by doing this. We can have complete coverage of the machines in our plant, and don't deploy experts on simple faults and simple machines. So use a tiered approach to cover all of our machine with dwindling resources. And the next thing we're going to talk about is when to use vibration tools, because there are different types of faults on different types of assets in our plant. If you think about the power coming in, and then you've got your drives, you've got your motors, you've got your motor windings, you've got your rotating motor, you've got your pump. This is different links in a chain, and if one of those links would go, well, the entire machine goes down. So think about it. We may need to use electrical type tools to look for electrical faults. So look about scope meters and digital multimeters. On the rotating end, we're going to use mechanical, vibration, and laser alignment. And then thermography is used to cover both electrical and mechanical rotating machines. So, what tool do I use? Which one do I start with? Well, for rotating machinery, we like to use this this chart, this graph, and this chart that we were showing, the potential failure chart, is showing on a rotating machinery. Now, this is a conceptual chart. It's not graphed by time or machine or anything like that. But it's pretty well accepted in industry that if you've got a machine that starts to fail, there are different technologies we can use to find that failure, to identify that failure before it fails. Way over on the right, you can see the machine has failed. Before the machine fails, it's hot to the touch and there's audible noise. You can see that thermography can help us find it before it gets to the point where it's going to fail. But sometimes that could be a little late for rotating machinery. So this chart shows that for rotating machinery, vibration is really the best tool because we can find a fault. So once it's hot to the touch and once thermography can see it or it's making noise, the damage is already done to rotating machinery and there's already energy waste. But vibration is going to find that months in advance. Now, a lot of people use oil analysis and ultrasound. That's fine as well, but sometimes the ultrasound is too early. That's really meant to be at the time when it's time to grease the bearings. But we're going to show you that vibration is really the best tool for rotating machinery to find roller bearings when they need to be replaced and to be able to watch them as they go from good to bad and to find the right time to do that repair. So when to use which of these vibration tools? There are different types of vibration tools to do different tasks. So think about it as a screen, diagnose, correct, and then verify. So this slide does a real good job of showing how we would first use screening tools to find out which machines are good or bad. In this example, we're showing a vibration meter. You could also use a thermal imager. So after we find out which machines are good or bad, and these are simple go-no devices, easy to use, and we'll talk about that. We'll show you what we mean by one of these. Second, we would diagnose the faults. Just like the doctor would say, tell you what the problem is, and more importantly, what to do to fix it, and the root cause of what that problem is. An example down at the bottom, you can see, it might be a little small to read, but it says serious misalignment, and the recommendation is to align the machine. The next step is to correct the fault. So after we find we have a problem with a machine and we bump it up and we then diagnose what the fault is and we know what to do to fix it, well, now we've got to fix it. And today's laser alignment tools are very fast and efficient, a lot easier to use than they have been in the past, and they help the technician, the maintenance technician, be able to walk through the alignment job in a simple step-by-step process to quickly fix the alignment and get machines up and running as quick as possible. And finally, before you return the machine to service, let's make sure we fixed it. Let's make sure that not only did we fix it, did we fix the root cause? Because just replacing bearings and seals might not be the root cause. The root cause may be misalignment, for example. And if all we're doing is replacing bearings all the time, maybe we should look at using a vibration tester that'll give us the root cause of the problem. If it tells us it's misalignment, then let's use a simple alignment tool to correct the misalignment, and that way the bearings and seals last for years and years like they're supposed to. So verify it, make sure it's ready to go back into service. All right, let me take you through a real quick Vibration 101 to give you some basics of what is vibration testing. So if you think about vibration in its very basic form, and again, I'm not going to be able to get too detailed into this, but if you think of a weight on a spring vibrating up and down, as it goes up and down over time, it would make a sine wave. And that sine wave is showing us what the amplitude of the vibration is, how big the vibration is. Or sorry, that's how fast the vibration is cycling. But the vibration also has a magnitude, and that magnitude is the top of a peak to a bottom of a peak, and often it can be reported in any one of these three types, either peak, peak to peak, or RMS. The point here is not one is better than the other. Just make sure that you understand which of these you're using. Okay, so let's see how that works on a real rotating machine. So on a real rotating machine, if you've got some vibration of a rotating shaft, now keep in mind, even a healthy machine is going to have vibration. Think of this big heavy mass of metal rotating at 1775 RPM. It's going to make a lot of vibration, even if it's healthy. So the key isn't removing all vibration, it's learning which vibration is abnormal. So here we can see is as the heavy spot on the shaft rotates around, it's going to make a sine wave. And if the shaft is rotating at 1776 RPM, we're going to see a sine wave at 1776 cycles per minute. So as that heavy spot goes up and down, we're going to get a sine wave of vibration. And if you have other components on this shaft, let's say, for example, you've got 8 fan blades or 10 impeller vanes, as the impeller wave passes the vibration sensor that's typically mounted on the top of the machine or the side of the bearing, every time a impeller passes, you're going to get a little vibration event. So you can see in this example, we have a sine wave. This sine wave is making 10 cycles per revolution because there are 10 impellers on the shaft. And every time the shaft makes 1 revolution, we get 10 vibrations from the impellers. So you can see the sine wave is repeating a lot more frequently, but the amplitude is smaller. You're going to get a lot less vibration from the impeller, from a pump, than you would from this big heavy shaft. So that's really what vibration is all about. Vibration analysis is about identifying vibration peaks in the data to components inside the machine. So here we see 2 vibration peaks on top of each other. The big sine wave from the shaft vibration, the small sine wave that's repeating quickly for the 10 impeller vanes. And, you know, you would think that the 2 would be on top, would be, you know, you'd see both of those sine waves, but in the real world, they add on top of each other. So you can see the small sine wave rides on top of the big sine wave, and if we got 20 or 30 vibrations, the problem is it's a jumbled up mess, and it's hard to read. So the question is, without being a vibration expert, how do I read these things? Well, we do something, and again, I'm not going to get too deep into this, and don't worry, the vibration tester actually does this for you, but we convert it to something called a spectrum, and you'll hear vibration experts talk about the vibration spectrum. And basically all we do is we take this complex waveform and we separate the individual waveforms into a simple XY plot. So you can see the plot over on the right hand side is showing our 2 sine waves. Every sine wave has 2 components. A component of the speed, how fast it's repeating, and the amplitude. Over on the right, we can see the same thing. We can see a big peak that's turning at 1 cycle per second, or 1 cycle per revolution. That's our shaft vibration. And then we have one that's at a frequency of 10. That's our pump impeller. So don't worry if you don't get this. We went through this pretty fast, but that's really an overview of what vibration analysis is all about. Now, what we do in vibration analysis is that we've got to take all of these vibration peaks and identify them. So here you can see that all of the jumbled up vibration, we separate each of those individual vibration sine waves into a peak. And that's why a lot of time we look for these peaks. And each one of these peaks can be identified as a component inside the machine. Another way that we can look at vibration is called overall vibration. Overall vibration is much simpler. It's like taking all of those peaks and adding them up to just one number. And that one number is like an overall vibration. So think of that like your check engine light in your car. The check engine light says, hey, there's something wrong. You don't know what the problem is, but it tells you there's something to take a look at. And overall vibration is a tool that we can use for that because it gives us just one number. Instead of this really complex frequency waveform like an EKG that's hard to read, we get just one number. And that one number can tell us overall health of the machine. It doesn't tell us what's wrong with the machine, but a meter can use this to tell us, is this good or bad? Okay, so how do we use vibration analysis to identify problems in rotating machinery? Well, there's a couple different ways we could do this. One is we could go to a vibration course and spend 2 or 3 years and learn how to be a vibration expert. But what we've learned is that rotating machinery really aren't that much different from each other. If you think about it, a simple motor pump, from a vibration standpoint, is really just a motor shaft with two bearings, a pump shaft with two bearings, and something hanging on the end. So if we're looking for common vibration problems, it really isn't that complicated. And a lot of vibration experts over the years have built a lot of rules and a lot of templates and baselines to help us to be able to identify the standard machines. So we can simplify when we look at a machine. Now, we're not going to be able to simplify when we look at machines like turbine generators or gas turbines or paper machines. Those kind of machines, we're still going to have to use a vibration expert because there's just too much variation. But in simple standard machines, they're pretty basic, and there really isn't that much different from a motor pump and another motor pump. So when we look at a machine, there's really only 5 or 6 differences. One is a motor by itself, and so here you can see an example of on the left of a cutaway drawing of a motor pump. In the middle is a 3D image of a motor standalone, and then over on the right is how we would take the vibration measurements with a vibration tester. So one type of basic machine would be a motor standalone. Another couple of motor types would be a direct drive or motor close coupled machine, where the pump or the fan impeller is mounted directly on the motor shaft, where here you just have the motor bearings. Another one is a coupled motor. So you've got a motor shaft with two bearings and a pump shaft with two bearings and a coupling in between. Both shafts going the same speed, but you would take a measurement from the motor bearing and a measurement from the pump bearing. The other types of machines are you could have a solid coupled machine or a belt-driven machine. So a belt-driven machine would have a motor shaft going one speed and a fan shaft or a pump shaft going a different speed. So as you can see, this machine is a little bit more complicated, but again, the machine is probably running about the same, and once we know what the ratio is between the motor shaft and the pump shaft, it's pretty easy to diagnose faults from this machine. And then the final type of machine would be a gearbox machine, a gear-reduced machine. Again, similar to the belt-driven machine, where the motor shaft is going one speed, the output shaft, the pump or the fan, is going a different speed. And if we know the speed of the motor and the speed of the pump, then it's pretty easy to diagnose faults with that. The most complicated machine that we're going to be able to do with an automated vibration diagnostic system is a motor-coupled, belt-driven machine. And even though this seems very complicated, once we understand the different ratios of the speeds and tell that to our vibration tester, it's able to diagnose this machine for us. So what is being driven? Okay, so the different pumps will have slightly different vibrations, and so we're going to want to identify what type of pump we have. So is it a centrifugal pump or propeller pump, a piston pump? Over the years, vibration experts have categorized the vibrations seen from different types of pumps. So how do these different machines, how would we set them up with different tools? So we've talked about the vibration meter. So the vibration meter is simply going to take an overall vibration reader. Think of it like the nurse. It's going to simply tell us, is the machine good or bad? The vibration tester, and so with the vibration meter, it's easy to set up. You take a quick overall vibration reading. It takes a second or two, and it's done. The tester is going to diagnose the machine for us, but it's going to take a little bit more data. Typically, it's going to use a triaxial sensor, and we're going to take a measurement from each motor bearing and 1 or 2 pump bearings. It's going to take about a minute per bearing. The analyzer requires an analyst to set it up, and if it's a very complicated machine with a lot of variables, then this vibration expert is typically going to use a single channel sensor and take a measurement from the 3 different axes on each bearing on the machine. So it'll take a little bit longer, and you need an expert to be able to do that. So what are these 3 different devices going to give us for results? The meter is going to give us the general health of the machine, but it's going to give us that answer in seconds. So we're going to walk around with a meter and take a quick snapshot of our machine just to find out if they're good or bad. The vibration tester on the other side is going to take about 5 minutes, but it's going to give us the answer. It's going to tell us what's wrong with the machine, how severe that fault is, and more importantly, what to do to fix it. And then finally, the analyzer. The analyzer is going to give us a detailed analysis on complex problems or on complex machines, but it takes longer, 30 to 40 minutes on a machine, even if it's healthy. So that's why we don't want to send out an expert and an analyzer for standard machines, and we sure don't want to analyze healthy machines. So use the right tool for the right application. So let's start by talking real quickly and run through how to use a vibration meter to screen the health of rotating machines. So remember, we talked earlier that overall vibration is just the overall noise of a machine, all the vibration of the machine. It's just a simple number. It's not going to tell us any detail about the machine, but all we want to know is the machine good or bad? A high vibration is going to tell us we've probably got a problem. A low vibration, the machine is probably okay. So we would trend this over time, and once it started getting high, we know something is wrong with this machine. So some of the limitations of overall vibration is that different machines can have different vibration levels. So one solution to this is to get a database of overall vibration levels for some standard machines. So here in this example, down at the bottom, we're showing how we could trend a machine over time, but it would take us time to find the answer. But if we knew what good vibration levels were for our specific reciprocating compressor, for example, then we would know if that number, 0.42, so 0.42 inches per second, you might not know, is that good for a machine? Well, it might be bad for a compressor. It might be good for a pump. We don't know. The other thing is bearings aren't going to be seen in the overall vibration. If you think about this big, heavy mass of metal, the shaft rotating, it's making a lot of vibration. Bearings are very low amplitude, but they're in a high frequency. So we can use a different technology. So here you can see down at the bottom, the screen of this bottom left, the overall vibration meter is actually going to take 3 measurements. It's going to take an overall vibration, which is the shaft vibration that tells us the health of the machine. But we also have to take a separate reading, which is our bearing frequency, which is higher frequency, to identify bearings. And then the last problem that we run into overall vibration is that it doesn't identify the fault. It simply tells us if the machine is good or bad. So the solution there is we have to, this meter actually is a way to signal to say it's time for further testing. So then you have to go use a vibration tester to find out what the fault is. Okay, so we talked a little bit about this high frequency measurement. We're using something called Crest Factor Plus. And Crest Factor Plus is a way of looking at that high frequency impacting. And, again, I'm not going to get into a lot of detail here, but what Crest Factor Plus looks for is that high frequency impacting of the bearing, and we can trend that over time, and it'll tell us whether the bearings are getting bad. Okay, if we look at a vibration meter, let's kind of put this all together. A vibration meter is really a screening tool. And here we see an example of a Fluke vibration meter, and you can see that we've put a few new things in the Fluke vibration meter. The tip of the meter is specially designed to get both low frequency and high frequency measurements. One of the issues with a vibration meter is if two people go out to take measurements, if you press into the vibration meter into your bearing too hard, you might get a different reading. So we've got a force sensor that makes the readings more repeatable. We talked about three measurements: overall vibration, bearing impacting, and temperature. But we really need to know, is this good or bad? So we use a severity scale based on real machine data to tell us, is that number 0.06 or 0.42, is that good or bad? Finally, we want this to be very rugged and something we can use out in the plant. And notice that out the bottom, there's a green light, and that green light is a way to tell us that we've given it enough force. You don't want to push in too hard, which affects your vibration readings, but you want to make sure you give it enough force to give a good reading. So as you push this meter into the bearing of your machine, then this green light will light up to tell you that you've given it enough force. Okay, to keep moving here, I'm going to run through this pretty quick. How do you set up a new machine? It's pretty easy. You simply give it a name. You tell it which of the 37 categories it is, and that's really all there is to it, because all you're telling this screening tool is, what is the name of my machine, and what type of machine do I need to compare it to know if the readings are good or bad. Now, here's a quick list of the 37 different machine categories, and you'll see that there's things like reciprocating chillers, there's belt-driven fans, direct drive fans, coupled fans, cooling tower drives, centrifugal pumps, both vertical and horizontal, positive displacement pumps, air compressors, rotary screw, reciprocating, multi-lobe blowers, even machine tools. So you can see, you pick which of these tool machine categories are closest to your machine, and then we would use real vibration data taken by real vibration experts to know if your machine is good or bad. How do you take a measurement? Pretty straightforward. You walk up to your machine, you press the point of the vibration meter into the bearing of the machine, typically one on the motor, one on the pump, or on the fan, and take a quick measurement. How do you read the results? Pretty straightforward. You're going to get three numbers. You're going to get a overall vibration number, you're going to get a bearing impacting number, and a bearing temperature number. It's going to compare that to the overall, to the machine type that you have, and it's going to tell you whether the machine condition and the bearing condition are good, satisfactory, unsatisfactory, or unacceptable. If you get an unsatisfactory or unacceptable, what do? Well, you go get a vibration tester to find out what the fault is. What do you do if you see good or satisfactory? Nothing. The machine is healthy. So that's really what this tool is designed to do. Is the machine good or is it bad? Do I need further testing? Now, some of the database or some of the ways to track this in your software, you could use a simple Excel spreadsheet. So in Excel, we could trend the three readings: overall vibration, the temperature reading, and the bearing impacting number. In addition, we can compare this to the 37 machine categories to know whether it's good, satisfactory, unsatisfactory, unacceptable. We can also compare this to ISO standards. There's an ISO standard, 10816, that is used in general industries. It really only has 4 categories: small machines, medium machines, large machines, and large machines with a flexible foundation. So it's not as specific as the 37 categories, but it is an ISO standard, and it will help you determine whether the machine is healthy or not. And we have some information on the ISO standards. If you want more information, you can go to our website and download the ISO 10816. But it's a pretty standard, straightforward. Again, it's like your check engine light in your car. It simply tells you good or bad. It doesn't tell you what to do to fix it. Okay, so you can also take your measurement from your machine and you can save it up to the cloud. There's a web-based program that Fluke uses called Fluke Connect that allows you to share this database with other people in your company, or even send it on to consultants so they can take a look at it. What if you have a machine that it's hard to get the vibration meter into a tight place? Well, there's external sensors that you can plug in. These external sensors have a sensor with a magnet and a coiled cable. That way you can reach into tight places and take measurements from your vibration meter. Okay, so we went through the vibration meter, and remember, the vibration meter is simply going to tell you, is the machine good or bad? After you find out the machine is bad, now you need to call in a vibration tester, the doctor, to tell us what the fault is and what to do to fix it. So let's walk through the vibration tester. The vibration tester, like a doctor, is going to ask questions about the machine and take some further tests to find out if the machine, what the fault is. So think of it like an EKG. So we're going to take some frequency data. There's 3 simple steps: setup, measure, and diagnose. Think of setup like the questions your doctor asks when you go in. The doctor asks you, where does it hurt and when does it hurt? Same kind of thing. We're going to tell it some basic information about our machine. Then we're going to take measurements with a triaxial sensor. You can see the triaxial sensor over on the right. And then this tester is going to compare data to a database of hundreds of thousands of machines that are taken from real rotating machines, just like your machines. So how do we answer these questions? Pretty simple, pretty straightforward. There's a wizard that walks through that asks you questions. It knows which questions to ask, just like the doctor knows which questions to ask. So it's going to ask you questions about the motor, questions about the transmission, the coupling, and questions about your driven component. And when it does that, it's going to make a computer-generated image so that we know where to take our vibration measurements. So when we're out in the field, it can walk us through that step and to be able to take our measurements. So the first thing it's going to ask us is, what is the speed of the rotating shaft? Because in vibration testing, the most important thing is I need to know the speed of that big heavy shaft rotating. It's, I need to know how fast it's going. That's the most important thing for the automated diagnostic system. It's the same thing that a human analyst would need. When you go see the doctor, you don't expect the doctor to find a problem unless you tell him where it hurts. So we need to find the speed. So the speed can be found by using a laser tachometer. Laser tachometer is nice, but it requires you to put a piece of reflective tape on the shaft. You could use a contact tachometer, but that means that you're going to have to touch the shaft, and in a lot of places that's not safe. You could use a stroboscope. A stroboscope is a flashing light that allows you, without contact and without using a piece of reflective tape, to find the speed of the machine. Although this isn't going to be able to be used on real low-speed machines because the flash isn't going to give us enough light. You could also go to the variable frequency drive panel. Now on constant speed machines, you don't have to do any of this. You just go to the nameplate and find the speed of the motor. Okay, so why is a stroboscope used? Well, we kind of talked about a couple reasons why. You can use it to find the speed of a machine, and it allows us to do it without having to contact the machine, and also without having to use a reflective tape. There are other uses for a stroboscope. You can find the different speeds in bottling lines. You can find speeds on belt-driven machines. You can find machining problems, problems with paper lines, all kinds of different things. What does it do? It's simply by adjusting the flash rate of the strobe, it allows us to freeze a process or a machine. Okay, so to build a machine, I'm not going to spend a lot of time here, but I'm going to show you what this looks like. But basically, it's going to take you through a series of questions about the machine, kind of things that you know about your machine. Is it AC or DC motor? Does it have a variable frequency drive? What is the RPM? What is the horsepower? And is it horizontal or vertical? And then does it have roller bearings or journal bearings? And we're going to help you out by telling you, if you don't know, what should it be. Step number 2 is to take measurement. So we put this triaxial sensor on the bearing of the machine, and the vibration from the rotating shaft transmits through the bearing into the bearing housing and into our sensor. We attach this sensor to the machine by using a very strong magnet, and that's how we take our vibration measurements. Where to mount the sensor on the machine? It doesn't really matter as long as we can get a good solid metal surface with a magnet. So you're going to be careful of thin metal, and you're going to be careful of motor fins and that kind of stuff. So you simply mount you mount the sensor on the bearing of the motor, and you take 2 quick measurements, and then it diagnoses it for you. In our training manual, we talk about where not to put the sensor. So these are actual slide captures of our training manual. In our training manual, we show you where to take your measurements, where it's good, where it's not so good. The tester walks you through and tells you, okay, on bearing number 2, mount the sensor. After you mount the sensor, it's going to ask you, is your sensor on the top side or end of the machine, and is the cable perpendicular to the shaft? The reason we ask this is we're using a triaxial sensor that measures data in all 3 directions simultaneously. This saves us time, and it's also much easier. When you're all done, you press the diagnose button, and it automatically diagnoses your machine for you based on similar machines that we've analyzed data on, and it'll tell you, just like a human analyst, it's going to look at the vibration patterns inside the data, and because it already has seen these patterns on other similar machines, it knows how to determine the faults. There are really 4 faults with rotating machinery: imbalance, misalignment, looseness, and bearing failures. Even though the vibration tester can diagnose over 4,700 faults, these 4 faults are really the ones that you're going to see on a daily basis, and we don't want to, and these are the ones that we're going to worry about. So the automated diagnostic system, these vibration peaks, runs them through an automated software program that in 3 or 4 minutes is going to tell you what's wrong with the machine, how bad that fault is, and what to do to fix it. We've taken a high-end vibration analyzer and made it easy to use to walk you through the process and give you answers, not a bunch of data or numbers. And so in our training, we would show you how to use this tester. Basically, you review the results. Why do we want you to review the results? Garbage in is garbage out. An automated diagnostic system is very, very good, but it's not a black box. And if you take wrong data, you're going to get bad results. So we're going to teach you how to review the results and how to be able to review the report, because that's the job of the maintenance technician, is to give it good information, take good measurements, and then review the results before you approve the work order and go out and do the work. Okay, ran out of time, so we also want to talk a little bit about how to set up a vibration program. Some of the hints we'll give you are start small and grow. The number one killer of a new program is trying to start too big and the program never gets started. Start with 25 or 30 machines, get some successes, document some successes, and get the program started, and then you'll get more buy-in to grow the program. Which technology do I start with? The number one killer of a program is start with just one technology and then trying to analyze every machine using that one technology. It doesn't work. Use the right technology for the right problem. Use vibration for rotating machines. Use electrical testers for electrical problems. Use infrared imagers to support the mechanical and the electrical. And then finally, what do you do with all the data? The number one killer of a program that's been running is data overload. So you need to get answers from the data. And I think we've shown you today that by using vibration meters and vibration testers, we're going to get the answers we need from the data and not just a bunch of data. All right, so last slides we'll talk about here is why is a vibration meter needed? It's to be able to screen a machine and find out if the machine is healthy. And we talked today about how the vibration screening tool is 5 tools in one. It's going to look for overall vibration, it's going to look for bearing impacting, and it's going to look for the temperature of the bearing. It's also going to give you the health of the bearing and the overall health of the machine. Just like a nurse, it's going to tell you whether the machine is good or bad. And the vibration tester, what is it used for? Well, it's used for knowing when a machine, what the fault is. Remember, there's 4 common faults: imbalance, misalignment, bearings, and looseness. And just like a doctor that diagnoses most problems, this is going to find 90% of the problems with standard machines that have very few variables. And the proven diagnostic program with 30 years of machine baselines is going to help you get your machines up and running. Okay, so we went 45 minutes, so that's the end. We're going to wrap it up, and I'm going to open it up to questions. So, Nicole,
thank you, John.
over to you.
Thank you. Yeah, we'll go through the questions now, and as a reminder, if you'd like to ask a question, you can send it through your question box in the webinar controls. And I know someone did ask if you'll be able to get a copy of the slides and the audio of the presentation, and the answer is yes. We will be sending that out probably later this week. Not today because half the office is stuck in a snowstorm. We're in upstate New York, but probably later this week. Let me see if I can expand this. Okay, everyone asked that. Let's see. How much training do I need to use the vibration tools?
Oh, good question. So, not a lot, but it varies. So if you think about the 3 tools we talked about, the vibration meter, the training is probably 15 to 30 minutes. You know, it's almost like watching a YouTube video. There really isn't much to learn because it's really easy to use, and really all you're learning is we probably taught you enough about the vibration meter already that you could go out and use it because it's just that easy. The stuff we covered today, you know enough about vibration to go out and use the vibration meter. The vibration tester, probably something like the range of 8 hours, you know. So after, we've got a training program that after you go through some exercises, because we want you to learn how to use this on some test machines before you try to use it on your real machines, and if you make some mistakes, then you kind of get a little bit aggravated. So we want you to, we've got an 8-hour training program, and that's pretty typical for a vibration tester, to learn the basics of how to set up the machine correctly, how to take measurements correctly, where to find the locations on machines, and how to review the reports. And so go through some exercises and learn, so first we learn, then we do some practice, then we go out and set up our real machine. So probably about 8 hours. The analyzer, on the other end, because it is an expert's tool, an analyzer, you're looking at 3 to 4 days of training, and then a few months later, probably another 3 or 4 days of training, and 6 months later, another 3 or 4 days of training, and it probably takes a good year or more before you're good enough to be able to go out and take measurements. You're probably 2 or 3 years before you're good enough to be able to analyze the data. So quite a range from the meter, which is 15 minutes, to the tester, which is 8 hours, to the analyzer, which is days or weeks or months. So quite a difference. All right, thanks, Nicole.
Okay, thanks. Here's another question. Can you speak to velocity measurement versus acceleration measurement? Is the analyzer looking at acceleration?
That's a good. So both, actually, all three of the tools are measuring acceleration and then converting it to velocity. So if you think about this, what that means for the layman is the amount of vibration that a shaft moves up and down, we call that displacement. The amount of vibration movement over time, the sine wave, is velocity. A change in velocity over time is acceleration. The reason we use acceleration is because we can use accelerometers. The sensors that we use for vibration are accelerometers. And accelerometers is a crystal, and there's no moving parts, which means there's nothing to break, nothing to wear down over the years. Velocity meters are a coil and a magnet, and it's moving up and down, and anything that moves is going to wear out and break. So the industry has stopped using velocity meters many years ago, and so the answer is we use accelerometers to measure the vibration, and then we convert it typically to velocity, because velocity is really the motion up and down, and that's the fatigue, that's the wear, that's where the faults are seen in the velocity. All right. Thanks, Nicole.
Okay. This gentleman said, we are interested in the calibration process involved in vibration tables. Can we help?
Calibration, there's a calibration of the sensor, and the vibration tables, so I guess I'm not quite sure what the question is.
We'll reach out to him afterwards and make sure we answer his question.
Yeah, because I don't quite understand the question, but if you're talking about calibration, yes, well, that's one thing. The good thing about accelerometers is it's a crystal, and they don't change. They're good for 10 or 15 years. So in reality, an accelerometer doesn't have to be calibrated. I mean, there's nothing to calibrate, actually. It's either good or it's bad. So really, every couple of years, you could check the calibration, but let's face it, you're going to know if it isn't working because you're not going to get any more readings. If the crystal is cracked, it's either good or it's bad. So in reality, you really don't need to calibrate an accelerometer any more than maybe every few years, because there's nothing to calibrate. But okay, we'll get a specific answer after, when we find out if that was even the right question.
Yep, that sounds good. When using the tester, is it advised to take only it says vertical, but I'm assuming it's vertical reading.
Vertical,
Only on the inboard? Does that make sense?
Right. Yes, it does. So in the past, vibration data collectors were kind of slow. And so vibration experts for years would kind of, it was a trade-off between complete data versus how long it took for time. So there's been a lot of studies over the years, and the U.S. Navy did a study probably 25 or 30 years ago, and they found that if you take vibration in just, because if you think about it, a rotating shaft is vibrating in three directions: up and down, side to side, and end to end. And if we just take vibration in one direction, we're not getting the whole picture. And since our vibration tester is an automated diagnostic system that's automatically diagnosing imbalance, misalignment, bearings, and looseness, it needs to know where the high vibration is coming from, as in, is it the motor bearing or the pump bearing? It also needs to know which direction the vibration is strongest to know whether it's imbalance or misalignment. If you only take it in one direction, vertical, you know you've got bad vibration, but you don't know what the fault is. So the answer is you need all three directions to be able to diagnose between imbalance or misalignment. So that's why a lot of the testers, I think most of the testers nowadays, are using triaxial sensors, because it's basically three sensors in one, which means I can measure the vertical, the horizontal, and the axial all at the same time. They're all simultaneous, and that way it's much faster, and I get a complete picture of what's going on with the machine.
Thank you. All right, I think we have two more questions. Let me see. Does Fluke offer more advanced vibration analysis equipment? We test and repair gas and steam turbine generators. Our generator specialist is a analysis-trained engineer. So I guess the question is, are there more advanced tools?
There are more advanced tools, but I think at the beginning of the question asked, does Fluke offer them? No, we don't, because Fluke, you know, we provide tools for non-experts to try to make it easy for a technician to be able to do some of their own work. So a generator of this type of needs an analyzer. You're absolutely correct, and Fluke doesn't make analyzers, but there are other tools out there that are designed exactly for that application. And like we showed you in the slide where you see the machine pyramid, machines at the top of the pyramid, like generators and engines and stuff like that, require an analyzer and require somebody with a lot more vibration training, and also some more sophisticated software that allow you to do a lot more than just the basics that a vibration tester would do.
Okay. When measuring vibration for pumps, you mentioned that it is the number of vanes that pass for each rotation. How does this apply for a multi-stage pump? Is this multiplied by both the number of vanes and the number of stages to display the frequency at which it's vibrating?
Yeah, that's a good question. So if you think about it, the vibration seen as the shaft rotates around, you multiply by the number of impeller vanes. But multi-stage pumps, thankfully, most multi-stage pumps are going to have the same number of impellers per stage. So, for example, if you look at a boiler feed pump, it might have 5 or 6 different impellers, but each one of them would have 5 impeller vanes. So we're still going to be looking at 5 because each one of the impellers has 5. So the answer is no, you don't multiply 5 times the number of stages. If they're all 5, then 5 is your number. Now, if you have a multi-stage pump that has different stages, like 3 of the stages have 4 impellers and 3 of the stages have 5 impellers, you're going to have to look at both 4 and at 5. The high vibration is at 4 is going to be from one of the impellers with one of the stages with 4 impellers. The high peak at 5 would be from one of the stages that have 5 impeller vanes. So it's just whatever the number of the impeller is.
Okay. We're going to take one last question, and then any further questions we'll get to afterwards. We can address after the webinar. So let me read this one. It's a little detailed. Is the vibration meter appropriate for using on Pratt & Whitney 9-cylinder radial engine used on DHC Beaver aircraft? Looking for a cylinder about ready to crack.
I would say probably not, because vibration meters are really designed for industrial machines, because they've been designed to look for more standard types of machines: motors, pumps, fans, compressors, blowers. They'll be able to be used a little bit into some of the machine tools, but when you start looking at some of the you know, the high speed turbine engines and stuff like that, the tolerances are very, very close. The vibration levels are very, very small, a lot different than a you know, a centrifugal pump or a rotating fan or something like that. So I would say that's probably not a good application. You're going to need something. You're probably going to have to go to a vibration analyzer for that, because the vibration meter is, I'm afraid, not going to have the tolerances or the clearances or be accurate enough to be able to do that.
All right. Part 2 of this was, how about on vacuum pumps mounted on the aircraft engine case? The shafts usually shear off during use.
That one is a little bit closer, you know, especially in a test, you know, where you're testing a vacuum pump or something, you know, in a shop or something. I think we could probably do that with a meter. You might even be able to do that on the pump, on the engine itself. You're getting a little bit into the gray area, so we wouldn't guarantee it, because it's, you know, really was designed for industrial and facility machines. But you know, I would say maybe give it a shot, see what you find. But definitely not on the gas turbine engine, but maybe on some of the vacuum pumps.
Okay, thanks, John. And thanks, everyone, for attending today. That concludes our time. If you have further questions or would like to find out more about our product and service offerings, you can contact Transcat at 800-800-5001, on the web at transcat.com, or you can email me directly. My name is Nicole Van Wert. My email is nvanwert@transcat.com, and that'll be sent out along with a copy of the presentation as well. Thanks, everyone, for joining us, and we hope you got something out of today's presentation. I do think it was valuable, and there were great questions. And I hope you continue to join us for future Transcat e-learning webinars. Thanks, John.
Thank you. Take care. Bye-bye.
Bye-bye.